Hello, this is the first part of chapter 4.3, and we will talk about linearly dependent sets and bases. So we discussed in previous chapters that we can actually define vector set, vector space by the set of the vector. We can span the space with the vectors. And, we don't have like reason to get the smaller number of vectors. We can take a bunch of vectors, and if it's too much, that's not a big deal, isn't it? We can span the vector with more vector than absolutely necessary. But if you write a computer code when every computation matters, having this large, overwhelmingly excessive number of vectors might be not the best idea. Your code will run forever. So how we can find the minimum number of vectors needed to span a vector space? And this is where idea of linear independency can be really, really useful. And just to remind you that the set of vectors is said to be linearly independent if there is such weights which makes the linear combination equal 0, or the vector equations of linear combination of the vector from v1 to vp would be equal 0. And probably it's not the easiest definition for you to grasp the importance, but probably the graphical explanation a little bit easier. We need to remember that for example, for two-dimensional space, our dependent vectors align on the same line versus independent are not in the same. And we can extend it to the three-dimensional space when the dependent vectors align on the same plane. So basically, our dependent vectors can be expressed in terms of each other. So the length of our vector into D of dependent vector will be proportional to each other, which makes it easier to identify and get rid of them because they are excessive using theorem 4. So if we have an index set of vectors, then we guarantee that if one of the vectors is linear dependent, it can be expressed as the linear combinations of other vectors. So you can just go through your vectors one by one and see if any given vector can express a linear combination of other. And if it does, we can get rid of it. We don't need that vector. For example, if you're working with it 2 dimensions, you don't need in your span space 2 vectors which is proportional to each other. Okay, and when we get rid of all these unnecessary vectors or linearly dependent vectors, we end up with a minimal set of vectors needed to represent our vector space. And that vector space we'll call a basis for the vector space. And it's usually, not usually, it's actually necessary to be a linear combinations of vectors. And this linear combination will be essential and absolute and enough to span a given space. Okay, so let's look at the example. Let's take 3 vectors, v1, v2, and v3, and just try to figure out if those 3 vector forms a basis, or basically, is those 3 vector is absolutely necessary to describe a 3-dimensional space R3. And again, you can go from the simplest definition of linear dependencies and try to compare each pair of vector to see if one of them is the multiple of others, but that's exhausting. That you might young and you might do numbers better than me, but I would rather start with a matrix. So I'll take matrix which consists of 3 columns, which is the vectors v1, v2, v3, and I'll just try to write it down in the echelon form, starting from the first column, then working for the second column. And look, that's really nice. Each of column in our matrix A has a pivot element. So we have 3 pivot positions. That's really great because we know that such matrix definitely has an invertible. And then we can use the invertible matrix theorem, which tell us for the invertible matrix, there is the vectors form a linearly independent set, which give us the property 1 in the definition. We also know from the invertible matrix theorem that this in the invertible matrix, the columns form a space which can be which span the whole space. So the property 2 is also stand through. So indeed, our vector v1, v2, and 3 form the basis in R3. Okay, and next time we talk a little bit more about the basis. And right now I would like you to go to the end of the chapter and start practicing.